Welcome to STEM Baba. In this video, we'll discuss the problem and conceptual exercises of chapter 4 from the book James Walker. So let's start. Now in this question, we are given that a certain projectile is launched with an initial speed v0. So this projectile is launched with an initial speed v0, and at its highest point, its speed becomes 1 over 2 v0. So let me draw the trajectory for this projectile. So this would be something like that, and at the highest point the speed becomes 1 over 2 v0. Now at the highest point, the direction of the velocity would be like this would be v, and at this point there is no component of velocity in the vertical direction, so we can say that vy is 0 at this point. And what would be vx at this point? This would be v0 cosine theta, which is same as this value, because in projectile motion the horizontal component of velocity remains same throughout the motion, as we have considered that there is no drag, air resistance. That is why this component always remains same. So at the highest point, what would be the speed? This would be the speed v0 cosine theta, and this is we are given that this is equals to 1 over 2 v0. So we can equate both these two things. This v0 and v0 will cancel, and from here cosine theta is 1 over 2, or we can say that theta would be equals to 60 degrees. Therefore this angle theta is 60 degrees, and this option C is correct. Now this question is a conceptual question, and it says that we have three projectiles A, B and C that are launched with different initial speed so that they reach the same maximum height. So maximum height for projectile A is equals to the maximum height for projectile B, and it equals to hc, that you can see from this image. The maximum height attained for these three projectiles is same. Now they are launched with different initial speed. So let the initial speed for projectile A is VA, for B is VB, and finally for C is VC. Now there are two parts in this question that we need to solve. In the A part, we need to rank the projectile in the increasing order of their initial speed, and in the B part, in the increasing order of their time of flight. So we'll start with part A. Now from this figure, we can easily tell that the rank for the projectile C is maximum. Rank for C is greater than the rank of B is greater than the rank of A. Least we have the rank A, and maximum we have rank C. Okay, now since the maximum height is same, so we can say that the initial vertical component of velocity is same, because maximum height, let me write this, maximum height, it depends on initial vertical component of velocity. And since maximum height is same for these three cases, so initial vertical component of velocity will be same for these three projectiles. Now since the longest range is for the projectile C, that means its horizontal speed would be maximum. So we can say that v0 x for projectile C will be greater than v0 x for projectile B, and will be greater than v0 x for projectile A, since range is maximum and the vertical component is same. Thus we can say that the speed for projectile C is greater than the speed of projectile B is greater than the speed of projectile A. And since we have to write the answer in the increasing order, so we can rewrite this thing as VA is less than VB is less than VC. So this will be the answer for the A part. Now next, in the B part, we have to rank in the increasing order of their time of flight. Now the time of flight is longest for the projectile that have the highest vertical component of the initial velocity, and in this case they have the same maximum height, therefore the same initial vertical speed. Thus we can say that the time of flight TA will be equals to TB will be equals to TC. This is conceptually. If you want to verify this answer by using the formulas that we derived, we can prove it from that point of view also. So let's try to prove these results by using the formulas that we derived. Now we'll prove A part first. Now we studied that range is V naught square over G sine 2 theta. Sine 2 theta we can write 2 times cosine theta sine theta, and we can rewrite this thing as 2 times V naught cosine theta times V naught sine theta divided by G. Now this V naught sine theta, this is the vertical component, initial vertical component, which is same for all the three projectiles. G is constant, 2 is constant. Now the range is maximum for which case? For the case C. So we can say that the V naught cosine theta would be maximum for which case? Case 3 or case C basically. So V naught cosine theta for the projectile C will be maximum. So this will be greater than V naught cosine theta for B, then greater than V naught cosine theta for A. Now speed is basically what? Under root V naught cosine theta whole square plus V naught sine theta whole square. This is the initial speed. We can write this way. And since this value is same, so we can neglect this, and this value is greater for part C or for projectile C. Thus the V naught for projectile C is greater than the V naught for projectile B, and finally this is greater than the for the projectile A. So this is we prove it mathematically or by using the formulas. And for the part B, the time of flight we studied, this is T equals to 2 V naught sine theta divided by G. Now 2 and G is constant. V naught sine theta is the vertical component of the velocity, which is same for all the three projectiles because the maximum height is same. Thus for this case, this TA is equals to TB is equals to TC. So we have proved mathematically also, and we have proved conceptually also. So in this question we are given that a second baseman tosses the ball to the first baseman, who catches it at the same level from it was thrown. So this player throws the ball like this, and it catch by this first baseman at the same level. Now the ball was thrown at an initial speed of 18.0 meter per second and at an angle 37.5 degrees above horizontal. Now there are two parts in this question that we need to solve. In the A part, we need to find the horizontal component of the ball's velocity just before it was caught. Now we know that the horizontal component of velocity remains same at all the time. So this is the initial horizontal velocity V naught, and its x component would be V naught cosine theta, and this value remains constant. So it's pretty simple. Answer for the A part would be 18 cosine 37.5 degrees, which comes out to be as 14.3 meter per second. So this is the horizontal component of velocity just before it was caught. Now next, in the B part, we need to find the time of flight. So it's pretty simple. We can use this equation: y equals to y naught plus v naught y times t plus 1 over 2 ayt square. Other way around, you can use the formula that we have derived for the time of flight, but I'm doing it from the basics. So y naught is 0. This is also 0 because we have taken this to be as our origin. This is the initial point. Y naught is 0, and y here, y is also 0, and v naught y is v naught sine theta times t plus 1 over 2 ay is minus g in this case times t square, and that is equals to 0. From here we can easily find the value of t. So 0 equals to v naught is 18, sine theta is 37.5 multiplied with time, this we have to calculate, minus 1 over 2 g is 9.81, t we have to calculate. We can solve it for t, and the value of t from here comes out to be as 2.23 seconds. So this is the answer for the B part. Other way around, you can use the direct formula that we derived: t equals to 2 v naught sine theta divided by g. Either use this formula directly, or you can start from the basics also. Now in this question we are given that in a game of basketball, a forward makes a bounce pass to the center and the ball is thrown with an initial speed of 4.3 meter per second at an angle 15 degrees below horizontal. So let me show it on the figure. So this is the ball thrown like this, and this angle is 15 degrees below horizontal, and the speed is 4.3 meter per second. Now the ball is released 0.80 meter above the floor. So this height h is given to be 0.80 meter. Now we have to find the horizontal distance traveled by the ball before bouncing. So the trajectory for the ball would be something like that. It would move like this, and then from this point it will bounce back. Now we have to calculate this distance x. This is what they are asking. Now it's pretty simple. X is equals to v0 x times t, and v0 x we have v0 cosine theta multiplied with t, but we don't have the value of this t. For that, we're going to see the motion of the ball in the vertical direction. For this, we can use this equation y equals to y0 plus v0 y times t plus 1 over 2 a y t square. Now the final position becomes 0. So here this is the final position, it becomes 0. Initial position we have h, which is equals to 0.80 meter plus v0 y. Now v0 y is in the downward direction. This is v0 y, which is equals to v0 sine theta. Now since it is downward and we have taken the upward value to be positive, so it should be minus v0 sine theta, and v0 we have minus 4.3, sine theta is 15 degree. So we can put it here. This would be minus 4.3 sine 15 degree multiplied with t, then plus 1 over 2 a is minus g, which is minus 9.81 meter per second squared multiplied with t square. Now on further solving, we'll get 0 is equals to 0.80 meter minus 1.1 meter per second minus 4.905 meter per second squared times t square. And I missed t here. This should be multiplied with t. Now it's a quadratic equation, so you can use your calculator to solve it for t, and the value of t from here comes out to be as t equals to minus 0.53 seconds and t equals to 0.31 second. So this value is neglected, and we have to take this value. Now we can put it here to find the value of x. So x equals to v0 is 4.3 meter per second multiplied with cosine theta is 15 degree, and time is 0.31 seconds. So on solving this, we'll get the value to be 1.3 meter. Therefore the horizontal distance traveled by the ball before bouncing is 1.3 meter.